start off with a launch. It says f of x equals 2 times the quantity x minus 3 times x minus 5 times x minus 4, the quantity squared. I'm going to give you about 2 minutes, and I want you to try to answer A, B, C, and D. See what you can come up with on your own. All right, 30 seconds. Discuss at your table. See if there's somebody who could answer a part that you couldn't. All right, letter A. What are the zeros? Can somebody tell us? What were the zeros? Yeah, Becca? 3, 5, and 4. Now remember, if you want to find the zeros, that's where f of x or y is 0. So does it make any sense to say 2 is 0? No. What did we talk about before? What happens to that 2 technically? If it's equal to 0, what's happening with the 2? Well, couldn't we divide both sides by the 2 and cancel it out? Because that's where it goes, okay? So in case you were wondering, wiring minds. And letter B, this one's an interesting one. This is really seeing if we can apply what we know. Anybody want to tackle B? What is the degree? Yeah, Kelly? I can tell it's definitely more than the second because I have an x and x, and then I have a quantity x minus 4 squared. Lilia, what did you think? You thought it was quadratic, Andrew? It's actually the 4th degree, okay? It's the 4th degree, and the reason why is even though I didn't multiply it all the way out, do you see if I just took the x times the x times the x squared, that is going to land, when I'm done multiplying it all the way out, to an x to the 4th. Without doing all of the work, I can get that much. All right, the roots are the same as the zeros. Okay, the roots are the same as the zeros. How many roots should f of x have? Well, it should actually have 4 roots, and it does, okay? The number of roots equals the degree. The number of roots equals the degree. And I want you to think about it because the roots were x equals 3, x equals 5, x equals 4, and we did have x equals 4 twice. But when it's there twice, we don't write it twice, okay? Later, we're gonna talk about what that means. It's called multiplicity. But I'm just planting some seeds right now for something that's coming. So those are things that we know so far. We know how to find the zeros, and we know how to find the degree of a polynomial. Polynomials with degree 3 or higher are called higher degree polynomials. So let's use our highlighters and let's highlight that. Polynomials with degree 3 or higher are called higher degree polynomials, and that's the name of our section. Frequently, third degree polynomials are associated with volume measures, and the reason why is volume is three-dimensional. So you're going to have a length, a width, and a height, and we're going to revisit the box, okay? Recall the box problem from yesterday. Here's a new example of a box. If we had a square piece of cardboard that is 30 inches by 30 inches, so it's a square, 30 by 30, the diagram shows if I cut a square of X inches from each corner, what I want you to notice, and let's use our highlighter, the sides would be 30 minus 2x, and the height would be X inches, because I'm folding it up. Remember this? So this time it would be a square, but I folded it up X inches. So that is, in fact, my height. So if I want to write an equation to represent the volume, I'm going to write 30 minus 2x times 30 minus 2x times x. This is called factored form. What I would like you to do, and I'm going to give you about a 2-minute head start, I would like you to expand this and put it in general form. So do the FOIL, okay, do the FOIL and get an answer, collect like terms, then multiply it by that x, which represents the height of our open box. So go ahead and try it. All right, so then when I do this, then general form is highest power to lowest power. So when you're done, check to see if your final answer matches mine, that v equals 4x cubed minus 120x squared plus 900x. So all I did is I FOILed 30 minus 2x times 30 minus 2x. I got 900 minus 60x minus 60x plus 4x squared. I collected my like terms and got 900 minus 120x plus 4x squared. And then I multiplied that by x. Ooh, I'm going to try that technique. Let's see if I can do it. Did you guys try it? Did you already know that? Convert. Isn't that cool? That's so cool. I think it doesn't like it when I put a box in it, though. Yeah, it didn't like my box. Does anybody know how to undo my box? Oh, thank you. Nice. Okay. I didn't know it could take just the box out. Okay, let's try this. Isn't that cool? Look how pretty that looks. It looks so pretty. Okay. Any questions on how you just expand it? It's the little things, right? It's the little things. Okay. So let's take a look now at the graph, and I have my graph is over here. So I'm going to introduce a lot of vocabulary. And so I'm going to slow down with 6.3. I initially thought I could do this in 2 days, and that was crazy talk. So we're going to actually do this over 4 days instead of 2. So I'm going to go nice and slowly. So I'm going to introduce some vocabulary. We have something called a local maximum. And what I would like you to write down next to this, a local maximum looks like a hill. Okay, I know this is not mathematical, but do you see that in this picture, I have a local maximum at 5, 2000. That's the local maximum. There's a hill. A local maximum means if you look a little to the left and a little to the right, this point is higher than the points a little left and a little right, or in that neighborhood. Sometimes it's referred to. This is the highest point in the neighborhood of points. Okay? I think a hill is a nice description. A local maximum is a valley. And it's like in that neighborhood, there's no points lower in that neighborhood. So if you see here on the graph, I have a local minimum at 15, 0. Extreme values are referring to maximums and minimums. So if you were ever asked, hey, look at this graph and tell me the extreme values, you would say the local max is 5, 2000. The local minimum is 15, 0. So this is new vocabulary. So we should do a little something to practice our vocabulary. I'm going to write myself a note. Do something to practice the vocabulary. All right, graphs of all polynomials with real coefficients have a y-intercept and possibly one or more x-intercepts. So on this one, do you see that the y-intercept is at 0, 0, which is also an x-intercept? And the x-intercepts are 0, 0, and 15, 0. Now we have other extreme values, and I teach AP Calculus, so we talk about extreme values, and we talk about local max and local mins, and then we also talk about what are called global. If I looked at the whole graph as a whole, is there a highest value? Is there one that's higher than all the others? No, because this really does continue forever, right? So it's shooting to infinity, and if you follow this to the left, it shoots down to negative infinity. So let's write something down here. Global extreme values are the highest or lowest of the entire graph. So let's jot this down. Global extreme values means the highest or lowest of the entire graph. In this one, there are no global extreme values because it shoots to infinity or shoots to negative infinity. Now I want to talk about, so let's jot that down. This graph has no global extreme values. Okay, this graph has no global extreme values. So when you think of globe, doesn't that think of like the whole world, right? So global is the whole graph. So maybe that connection can help us. I want to talk a moment about the zeros on this graph. My zeros are at x is 0 and x is 15. And I want you to notice something about this graph and the equation. So if I looked at what I wrote down, where if I set it equal to 0, I would have 0 equals x times the quantity, 30 minus 2x squared. Do you notice that at x equals 0, the graph crosses through the x-axis? And at x is 15, the graph bounces off the x-axis. And this is not an accident. Okay, this is not an accident. This is something that we're going to refer to as multiplicity. Anytime, do you see this 0 happens twice at x is 15? Because I have 2 of them, so it'd be like I got x is 15, x is 15. Anytime you have a 0 that has even multiplicity, that means it has an even power to it, it's going to do this. It's going to bounce off. And this is going to help us as we analyze graphs. But then, if I were to have, this is x to the first, if it had been x to the third or x to the fifth, odd powers, odd multiplicity, it's always going to pass through. We're going to do a really neat activity either Thursday or Friday called Guess My Graph, where I'm going to put a graph on your back, and you go around and you're going to ask questions. And then when people tell you the information, then you're going to try to sketch the graph on your back based on the information given. All right, let's carry on. So let's look at how volume increases and decreases throughout the graph. So we're looking above, and it says, what is the average change in the volume for x equals 0 to x equals 5? Well, average rate of change is slope. Average rate of change is slope. So you're going to use an Algebra 1 concept of y2 minus y1 over x2 minus x1. So I have the points 0, 0, and 5, 2000. Those are on our graph, right? We have those on the graph. So if I want to find the average change, I'm going to take y2 minus y1 over x2 minus x1. If you have a calculator, go ahead and grab it, and let's do the computation. So you're going to get 2,000 over 5, which is 4,000. And let's go look at my units. These were in inches, and so this is volume. So that's 400 inches cubed per inch. Okay, because I have volume over inches. Now, let's do the average change of volume for x equals 5 to x equals 15. So we knew it at 5, 2000. And then we have on the graph the point 15, 0. So the average change of the volume would be 0 minus 2,000 over 15 minus 5, which would be negative 200 inches cubed per inch of side length. What does the negative tell you about the change? It's decreasing, right? The negative rate of change means it's decreasing. And think about it, okay? This is really, really cool. This is really, really cool if you look at your graph, and this ties in. Boy, I'm planting some wonderful calculus seeds right now. So do you see from 0 to 5, it was increasing. The volume's increasing. And from 5 to 15, the volume's decreasing. Okay? That's cool. So the volume is changing faster from x equals 0 to 5 than from x equals 5 to 15. Yeah. Oh, sorry. Let me roll that down for you. I was doing an activity with my calculus class. Is that doing it? Yeah. Okay. Sorry about that. All right, another characteristic that we will study, and we did this previously, is called end behavior or long run behavior. This term refers to what happens to f of x as x takes on extreme positive and negative values. You can think about how the graph looks as you look to the left for extreme negative values. So I want you to circle this and write x approaches negative infinity. And when you look to the right for very large positive values, this is x goes to positive infinity, you're describing where does the graph go when x is moving left and what happens to y when x moves to the right. And I know we struggled with this a little bit previously. Remember we did end behavior with, we did it with exponentials, with logarithms, with square roots. We did that with a lot of different functions. All right, in the case of this cubic function, you would say as x increases, y also increases. As x decreases, y also decreases. The behavior of a polynomial in the long run is dominated by the term of the highest degree. So if you take a look here, where I have in blue is just, let's use our highlighter here. Blue is y equals 4x cubed, and in red is the volume formula we were working. So do you see that in blue, okay, I'm going to look at this one right here. Do you see as I go left, it's going down. And as I go right, it goes up. So even though my volume formula had a wiggle in it, the long run or end behavior still does the same thing as the 4x cubed. So we can sort of ignore the middle part, and I'm only interested sometimes in just what's happening in the long run. Then here's what's interesting is if you zoom out, you can see more of the end behavior, and if I zoom more and more, then they actually do. You can't even see the middle. So the danger, though, with a graphing calculator, okay, and I want you to write this down. Whoops. It is important to know what shape to expect. So a bad window doesn't mislead you. Okay, it is important to know what the end behavior and the general shape of a graph should be, so that if you put it on the graphing calculator and you don't see that, you just have a bad window. And there is a button on the graphing calculator that says under menu window, and you have to learn how to adjust that window. So let's talk a brief moment here. If I have y equals x cubed, and we actually did this in an earlier unit. You remember how we did our arms? We did x squared was up, up. Negative x squared was down, down. If I have x odd to the left, the graph goes down, and I go to the right, the graph goes up. We would write the end behavior as this. As x goes to the left, that's x goes to negative infinity, my graph goes down to negative infinity. As x goes to the right, my graph goes up. So this first piece is the x part is the left-right, the y part is the up-down. And there's a beautiful connection to domain and range. Okay, x's are the left-right motions. My y is my up and down. So now what happens if I put a negative in front of x cubed? It's going to flip it over. So then, as I move left, okay, as I move to the left, which is x goes to negative infinity, so think about x is going on my x-axis, okay? As x goes to negative infinity, I'm moving left, and I want to know now, is it going up or down? So what would you say on this graph? It goes up, so it's going to positive infinity. As x goes to the right, so that's on an x-axis, as I go to positive infinity, that's going to the right, where does the graph go? Down. There you go. That's all end behavior is. All right, let's try this next example, then we're going to pause there because I think our brains are getting pretty full at this point. So in example A, we're actually going to do something we did in 6.2. It says, find a polynomial function whose graph has x-intercepts at 3, 5, and negative 4, and has a y-intercept of 180. So I'm going to pause a moment and give you about 2 minutes. And we did this in 6.2. Go ahead and write the factor form with an A in it. Once you get the factored form with A in it, then plug in that extra point. The extra point is the y-intercept of 0, 180. Then you can determine the A value. Then there's your equation. While I'm trying to be patient and let you work, on 6.3 worksheet, you're going to have 3 school nights to work on that. So I will tell you today which problems you can do, and we'll break it up over 3 days. All right, I'm going to start this one. So I would have started with y equals a times x minus 3, x minus 5, x plus 4. Then you're going to use the point 0, 180. Did you get A was 3? Yes. All right, good job, good job. So then, here's my equation. Now it says, describe the features of the graph. So here we go. When it says, describe the features of the graph, let me tell you what that means. You want to do any extreme values. You want to describe end behavior. We already know on this one the x-intercept and y-intercept, so that's okay. We want to do something new called increasing and decreasing. And we're going to spend a little more time on the increasing, decreasing tomorrow. But this would be extreme values, end behavior, and increasing and decreasing. So let's do that. So I see a local maximum. It is at negative 1.395, comma 219.649. There's a local minimum. Where is the local minimum? Yep, 4.062, comma, negative 24.093. Let's describe the end behavior. The end behavior has 2 rows to it. Yeah, Angelo? No, end behavior is always as x goes to negative infinity and x goes to positive infinity. It's not local, not local. So I would say, as x goes to negative infinity, where does this graph go? Up or down? It goes down. So we write negative infinity. As x goes to positive infinity, that means to the right. Where does the graph go? It goes up to positive infinity. All right, so now this is the part that I don't expect you to really quite grasp completely today, and that's okay. We're going to spend 3 days on this. Do you notice that increasing means that the graph is rising? So there are 2 locations where this graph is rising. So I'm going to use a highlighter here. And my graph is rising until it hits that local maximum, and then it rises from the local minimum. Do you see that? This is where the graph is increasing. And the way that we describe increasing is by the x values. The way that we describe increasing is by the x values. So do you see it's at negative 1.395 to the left forever, if I'm talking about on my x-axis. So kind of stay with me, and again, I expect you to be a little confused, and that's okay, because you're really learning some good Algebra 2 today. So that's from negative infinity to negative 1.395, and then it happens again from 4.062, to infinity. So I'm using left-right descriptions. To do decreasing, I'm going to use a new color. And my decreasing is where the graph falls. Okay, decreasing is where the graph falls. And this happens from the maximum, the local maximum, to the local minimum. All right, when you have a moment, pull up